Okay. Looks like we have a lot of attendees. Okay, we're going to go ahead and get started. Hi, everyone. Welcome to our EGI Fall Webinar Series, Discussions and Insight from EGI. I'm Jennifer. I am the Marketing Specialist here at EGI. Today's presentation is titled Demystifying Hidden Hydrogen, What We Know and Don't Know About Natural Hydrogen. Today, we're going to be hearing from EGI research scientist, Dr. Eiichi Setoyama, with special guest, Dr. Bryony Richards. At the end, we'll have some time to answer questions that you may have. I'm now going to hand it off over to Dr. Setoyama. Enjoy.
Okay. Hello and welcome everyone. Thank you for joining us today. So I will start the presentation. Okay. So about a year ago, I gave a presentation on natural hydrogen and had this slide to demonstrate an increase in public's interest in natural hydrogen. And this is the data as of earlier this week. And there was a peak in the public interest in natural hydrogen in December last year. And the interest level has kind of stabilized over the last few months or 6 months. But the number of publications on natural hydrogen per year is still increasing. And also the papers on subject relevant to natural hydrogen is still increasing. And with the new project started in the last few years, we can expect more papers coming out in the next few years. So it's becoming more difficult really to keep up with the development in natural hydrogen research and also to get started with natural hydrogen research. And for this presentation, I'm assuming that the half of the audience is new to the field of natural hydrogen research. And probably a quarter of you has done some reading on natural hydrogen. And the other quarter probably know a lot about natural hydrogen. But I'm hoping that all of you will find some new information, even better answers to your questions you already have. And I'm hoping that this presentation will stimulate your creativity and imagination and helps you come up with new research ideas. So in this presentation, we will go through these 5 questions. So what natural hydrogen is, why we are studying natural hydrogen, and where you can find, we'll look at analogues of natural hydrogen systems, and under when we will look at natural hydrogen system component and process, because the timing of events is crucial to have accumulation of natural hydrogen. And we will look at briefly exploration workflow. And in this section, Bryony will share what we are doing at EGI under a project called Natural Hydrogen Knowledge Platform. And in this project, we are integrating data and information to understand how natural hydrogen systems work. And we are also analyzing technical feasibility of natural hydrogen exploration and production. And I'm hoping that there will be a lot of questions, comments, and suggestions. If you have any, please put them in Q&A that you should see in the top menu bar. Okay. So let's start with the definition of natural hydrogen. So natural hydrogen is hydrogen that occurs naturally in various environments, and they can be found in different forms, like dissolved or free gas, or in inclusion, or it could be adsorbed to clay minerals, for example. You may also heard a term geologic hydrogen. This is a specific member of natural hydrogen, which is confined to the subsurface. And these terms are used interchangeably, and I don't think people would mind if you use either of them. And natural hydrogen can be found in different areas. They are geographically widespread and found all over the globe. And this paper, Zugonic 2020, listed over 330 sites with hydrogen concentration over 10% by volume. And the number of such sites is increasing. So you see that the global distribution of natural hydrogen now, you can find them in they are found in South America and Africa, and all over the place now. When you compare natural hydrogen with manufactured or artificial hydrogen, people often use colors to describe them. So in such a color scheme, natural hydrogen is either white or gold, and natural hydrogen produced using stimulation is often called orange. And the manufactured ones, so those from unabated fossil fuels have darker color like black, gray, and brown. And if you add carbon capture, they become blue. And these low emission hydrogen generated using renewable energies often called green, yellow, pink. And currently, most of hydrogen, manufactured hydrogen, come from unabated fossil fuels. And in the future energy mix, the most of hydrogen is expected from low emission hydrogen. So you see that there's a huge gap with the current supply of hydrogen from low emission sources and the expected hydrogen in the future from low emission resources. And natural hydrogen would be a great addition if we can addition to a low emission hydrogen source. So this diagram is a little complicated, but before that, you might heard comments like there are various methods to produce hydrogen already, and the cost of manufactured hydrogen is already low and will decrease. So why are you looking at natural hydrogen? So yes, there are many ways to generate hydrogen now. So this diagram shows feedstock, so raw materials like natural gas, oil, bitumen, coal, and also a primary energy source to generate hydrogen using these technologies. And geologic hydrogen or natural hydrogen is placed here. However, these low emission hydrogen production technologies, their technology readiness levels are still low. They are not deployed at large commercial scale production. So they're available, but these technologies are not mature yet. Another thing is that in this diagram, at each step in this process, you increase carbon footprint, water footprint, mineral requirement, land requirement, and also you lose energy at each step. And natural hydrogen being a primary energy source, you can skip all these steps and provide hydrogen for the end use, for end uses. So there's a potential that natural hydrogen can provide low emission hydrogen with low carbon footprint and also with lower water footprint and mineral consumption, land use and land use. So I just want to look at carbon footprint, for example, a little closely because these numbers are carbon or GHG intensity, so greenhouse gas intensity. However, this intensity of natural hydrogen also depends on the composition of the gas coming out from the reservoir or wellhead. So what we want is a pure or high concentration of hydrogen because if the gas is associated with, for example, with methane, the GHG intensity will be much higher. So although we argue that natural hydrogen has a low carbon footprint, it really depends on the composition of the gas. And next, I want to look at the cost. So the cost of natural hydrogen production is expected to be below $1 per kilogram of hydrogen. However, it also depends on the composition of gas, but also other things like the distance to the market, well depth, and how many wells you'd need to drill to produce hydrogen. So the diagram on the right shows estimated cost of the per kilogram of hydrogen. And this, so the left, it shows this is the case where you produce hydrogen at the 10 times the scale of hydrogen production in Mali. And in the right, this one is the 60 times the production of hydrogen in Mali case. So as you kind of scale up the production by drilling more wells, you could increase, you might decrease the cost of hydrogen production, but it could be still higher than $1 per kilogram of hydrogen. So again, we need to be mindful when we use these numbers when we discuss natural hydrogen's advantage, because it really depends on many things. There are also some unknown risks, things that we still do not understand fully. So one of them is hydrogen cycle, and so all these processes happening beneath the crust or within the crust. So this paper was published recently. And it shows that in the crust or beneath the crust, there's a lot of water, groundwater, which is not included in the current water cycle. And as you see that, and this is where you have hydrogen, natural hydrogen generated through radiolysis or the redox reaction. So I think this is also the case with the hydrogen cycle. We still don't understand what's happening beneath the crust. And so with that understanding, we cannot really measure the impact on what's happening beneath the crust. So it is hydrology and the hydrogen cycle and also deep biosphere. And the hydrogen leakage can also have a huge impact on environment, and it could add up to, for example, climate crisis. So hydrogen leakage could increase the amount of methane, is on the left, and could also increase ozone. So again, we need to be mindful of these risks when we talk about natural hydrogen. But I'm not saying that we shouldn't study natural hydrogen because we don't understand these risks. What I'm saying is that we need to understand these risks and also to advance our understanding of natural hydrogen systems. So now I want to move on to where. So again, you might have heard comments like, I've never heard of wells with high concentration of hydrogen, or hydrogen cannot be trapped, or Borakibobo field in Mali must be one-off because hydrogen cannot be trapped. So if we limit to ourselves just to, for example, literatures in English, there are reports of natural hydrogen since actually 1930s, but this one is from 1962. And this paper published in 1980 already talked about geothermal hydrogen system. And then this paper kind of talked about industrial exploration of, for natural hydrogen. And there was already a paper calling our attention to take hydrogen more seriously. And the paper on Mali field was published in 2018, so it's been already 6 years. So I think these statements are correct, that we had a prejudice and we kind of decided not to look at hydrogen, and I think that's and I agree that's why we didn't really know about these wells with high concentration of hydrogen. Okay, now I would like to look at 3 analogues of natural hydrogen systems to look at these comments as well. So I will start with Mali. Okay, so I'm not repeat what you probably already know, but this is the only pilot project of commercialization of natural hydrogen and using it to generate and provide energy to the community. And the key geologic features here is these Jurassic dolerite seals, which is serving as effective seals trapping hydrogen under the ground. And another important feature is these fractures, which is compartmentalizing the dolerite and the reservoirs to trap hydrogen beneath the ground. And the reservoirs here are carbonates, sandstones, and also a potentially fractured basement. And hydrogen is generated from the basement and also the iron-rich sandstones found in these intervals. And I also want to bring your attention to the depth of wells. They are very shallow. The production well was around 100-meter deep. So again, here the seal is direct seals, reservoir, carbonate, sandstone, and potentially the fractured basement. Hydrogen is generated through water reduction and radiolysis. And an active hydrogen generation, or the dynamic recharge of hydrogen, is indicated by the stable reservoir pressure. The pressure has not decreased since the production of hydrogen here. Okay. Now let's look at Kansas, United States. So here the year of discovery. So it's 1982. So there was discovery, or so hydrogen concentration was already reported in 1980s here, and there are papers since then on natural hydrogen. Here the seal is different from Mali. So here the seal is shales, and the reservoirs are these carbonates, dolerite and dolomite and limestone, and also fractured basement. It seems that the hydrogen is generated in the basement through radiolysis and also water reaction. And again, I want to bring your attention to the depth of the well. So these are, again, shallow wells, which is probably a good thing because that can reduce, keep the production cost low. Okay, so I went through all these, and the hydrogen might also come from mantle here. There's like indication that 1.5% of helium is coming from mantle. Okay, now let's look at Australia. So, Mount KT1 is not the first well which reported, encountered hydrogen. It's actually, I think it's Maggie well here. And the difference is that so the hydrogen is a little low, and the concentration is a little lower than the other places, but the helium concentration is actually higher. So in Amadeus, this Amadeus Basin, the seal is again different. Here the seal is salt, and the reservoirs are sandstone and or quartzite and also fractured basement here. So the salt layer here is very thick. It's over a few hundred meters could be, and it's an effective seal, and a large amount of helium trapped under the seal indicates that the gas has been accumulating under the seal for millions of years. And this is a really nice picture, I think. So where the salt is pinching out, there's a leak of hydrogen and other gases, which you can see as a gas chimney here, potential gas chimney. And above this gas chimney, there's a hydrogen sieve detected. So I think it shows that how effective salt can be as a sieve. So as I mentioned, the seal is salt here, which is different from just two analogs we looked at. And also here, the gas is trapped, and so it seems that the salt is a really effective seal, and it can trap helium and potentially some of the hydrogen for millions of years. Okay, so we looked at some analogs and talked about the distribution we looked at the analogs and the non-hydrogen sites. So hydrogen can be trapped in subsurface, and it seems that Mali might not be the one-off case. We have more and more natural hydrogen systems reported all over the world. And I just put this figure just to show how diverse natural hydrogen systems can be in terms of depth and also rock types for reservoir and also seas and also generation processes. So now I'd like to look at some of the components of natural hydrogen systems. So I will start with source and generation. So Milkov listed 32 hydrogen generating processes, out of which 24 are abiotic. But for exploration, there are many papers listed 3 processes as the main ones. So the first one is redox reaction between iron-rich minerals and water, including serpentinization. And the second one is a radiolysis of water. And the third one is overmaturation or rate maturation of organic matter. And I've heard people asking about temperature. So here's the temperature. So for redox reactions, it's for serpentinization, especially it's between 20 to 350. Optimal temperature range is about, I think it's like 200 and 300 between. And radiolysis is temperature independent. And for the overmaturation of organic matter, it can happen between 100 and 600 degrees Celsius. But again, the optimum temperature is between, I think it's like 200 and 400. There are other processes which generate large volume of natural hydrogen, but they are not. But they are very hard, difficult to locate. So for exploration, we are not really looking at them. But yeah, but they could be, contributing hydrogen, like we saw in, the analogues we saw previously. So I just want to look at the generation rates first. So serpentinization rate. So as I said, that the optimum temperature range is between 250 and 300. And the reaction rate is also controlled by the surface area available for reaction, or the grain size can be. And also water chemistry. So pure water is better than brines. And you may have heard a comment like, unlike electrolysis, natural hydrogen stimulation does not require pure water. But this diagram clearly shows that, yes, serpentinization can happen with brine, but fresh and pure water is definitely better than seawater or salty water. So again, we can make such statement, but we need to be mindful that it depends on many things. It's case by case. So another thing, another important thing for exploration is source generation potential. We need to know how much hydrogen could be generated from per volume of rocks. So this diagram shows that. So these circles show like include minerals and also rocks, iron-rich rocks. And the stars are cold, and it shows that cores could have higher generation potential, which might be a surprise, but because we're not really, it's included as main generation potential, but people don't talk about this much. So I think coal is another really great source for natural hydrogen. And this is something that you probably already, if you are working for like a coal mining company or oil and gas company, you probably know where you can find such accumulation of coal where they might be overmatured already. So this is something you can already start looking at and search for places. So generation rates and potential and estimation of generation rates and potential is really crucial for exploration and stimulation. But there's no really fast and cheap way or established method to quickly estimate hydrogen generation potential of iron-rich rocks and organic matter. So I found this project very interesting. So I'm kind of following what they're doing right now. So let's look at migration. So hydrogen, some of the hydrogen and helium has to travel a long distance. Some of them come from lower mantle, so it's like it's close to 3,000 kilometers, and it can take from hundreds of millions of years to billions of years. But if we look at the surface of the Earth or above the crust, migration can happen through diffusion and advection. This shows, and the rate or the speed of migration really depends on the mode of movement or migration. So it can take over thousands of years through by diffusion through reservoirs and some of the cap rocks, but it can take only a day or two, a few days, if hydrogen is migrating through advection, especially if as dissolved in water. And the primary control on the mode of hydrogen migration is pore throat diameter. The pore throat diameter is space between grains. So like for example, in sandstone, with a porous sandstone, hydrogen would migrate by advection. But if you are in the tight rocks, the hydrogen would diffuse, move through such rock by diffusion. And there's no really uniform depth boundary for the mode of migration. It really depends on histology and fluid composition, pressure, and temperature. So it will vary from place to place. So accumulation. So this is very, so accumulation is another thing that is very different from hydrocarbon. So it seems that the hydrogen accumulating in reservoirs in natural hydrogen systems are much younger than petroleum system, hydrocarbons. For example, in Mali case, the age of hydrogen is estimated to be around 500 years. And in Australia, this is different basin. So in Amadeus, where helium and hydrogen is accumulated over, for millions of years, but they're not like hundreds of millions of years. That could be the case for hydrocarbons. And in other places, the age of hydrogen is again only a few thousands to hundreds of thousands of years. And if you are interested in, hydrogen's behavior in reservoirs and reaction between fluid, hydrogen, and minerals, there are already a lot of papers on hydrogen storage, and you might want to start looking at these projects which have already published really good papers on hydrogen in reservoirs. So. Okay, let's move on to exploration. So I'm not going to look at each steps of hydrogen exploration workflow. If you're interested in, I'd recommend reading this paper. This is really comprehensive. It goes through from how you should do field measurement, how you should do lab analysis, how you should do really come up with some models. So yeah, this paper is really a great starting point to learn about exploration. But I think we all agree that the exploration for natural hydrogen really needs to start with reconnaissance by gathering the information, putting them together, and learning about the area or regions of interest, and then do characterization of geology using the data already available, and then you might do some simple modeling for like petroleum hydrogen systems to really narrow down the areas. You might do further investigation, but you can also do before or concurrently with the reconnaissance. You can do SIP identification and then do a field measurement. to narrow down the areas for further exploration effort. So now I want to pass the control to Brownie.
Thank you.
Yeah.
Good morning, everybody. I'm going to give a brief overview of what we're doing in terms of imaging analysis and hydrogen at EGI. I am an advanced imaging expert here with a background from, I like to say, galaxies to gamma rays. That's the kind of spatial space I occupy. So for those who aren't very familiar with hyperspectral imaging, it's a fairly simple idea that's complex in practice, which is a little unfortunate. We mainly use satellites here to gather data. And our key satellite for hyperspectral imaging is Sentinel-2. I'll explain a little bit why later. However, we do like to cross-correlate across other satellite platforms to really understand what's going on and to double-check our data. The additional satellites we use where the data is available is Prisma, which is an Italian space agency satellite, Hyperion, and then Avaris. Avaris is a NASA plane that flies very high-resolution hyperspectral imaging. You can see in the diagram, this is actually Canyonlands in Utah, and I'm using it just to show how we do push broom measurements. Hyperspectral imaging is essentially a rainbow as opposed to RGB, and this kind of shows the differences between imaging techniques. So we're very used to seeing RGB images. Everything in this presentation is an RGB image when it's in color. And then we move from that, adding in new bandwidths to make a multispectral image. And that's under 37 discontinuous bands. And all that means is that there are gaps in information between the spectral bands. Hyperspectral imaging effectively removes those gaps and makes a continual spectrum of information. Obviously, this gives you an insane amount of data. I was saying the other day that one image from Avaris can be up to 35 gigabytes before pre-processing. So the other thing you really need is very good computing power, and that's why we're kind of seeing this revival of hyperspectral imaging. The other reason why we're starting to use it more is that hydrogen seeps are often in remote or hostile areas. We still want to study them. We still want to gain the knowledge from those seeps, but we can't obviously go to Mali, which currently has a lot of rebels and wars going on. Obviously, seeps in Russia, we're not going to go there at the moment. So we need to find another way to characterize these seeps. As I said, the main platforms we use are several satellites and also a NASA plane called Avaris. This allows us to remotely detect hydrogen seeps, not only to detect them, but to also quantifiably tell you the amount of hydrogen coming out of those seeps. And this is the key to where our research has differed from current papers or papers in the past. We're looking to develop more of these index-based methods in conjunction with live drones. That is our goal with this technology, and we'll be hopefully moving into that next year. I'd like to show you 3 different depressions with hyperspectral imaging. We were pretty shocked actually at how similar these depressions are or can be with hyperspectral imaging. Obviously, you can see some features on RGB imaging. You can normally see the depressions. Here is the Mali depression that a lot of people know. Russia has some very nice depressions, including extinct depressions. And then this is the São Francisco Basin in Brazil. And again, you can see these 3 hydrogen seeps with a possible larger seep surrounding them as well. Let's look at some of these Russian fairy circles. These are really interesting because they show both the active and what we're assuming is extinct seeps. These seeps have quite an active life. Eiichi mentioned that some of them are 500 or so years old. We're seeing changes in these seeps over decades. And that's mainly because the information from papers with data is over a decade older than our spectral information. However, we're seeing both key features and evolution of the seeps within that data. This is, again, an index that we've used to really pull out these extinct seeps. You can kind of see these ghostly white circles. And then another band math equation that we're using allows us to really look at the internal details within the seeps. You can actually see little fairy circles within the larger fairy circle, surrounded by fairy circles within a bigger fairy circle. So these are complex dynamic systems that are both young and very active. I'm going to carry out this slide with, we are not going to tell you exactly how we've done this. We are hoping to push out a publication within the next month on this. Those people who are part of our knowledge platform will get insights into that data before anybody else. So if you're very interested in knowing the ability to detect hydrogen, I would advise you to talk to Eiichi more about the platform. But in terms of showing you the data, we're going to call this the spectral hydrogen alteration ratio. And the thing we're doing is we're looking at surface changes in the environment that allow us to look at the dynamic systems below the ground, the subsurface, to try and understand how hydrogen is generated, how quickly it's generated, and how quickly it disperses on the surface. It also gives us really good insights into the chemistry behind this. What chemical reactions are we actually looking at? Can we prove them from superficial changes? The data from the red sort of lines are from Larin et al., and that's in 2015. The study data is from 2024, so that is a 9-year difference in data. However, as you can see from the profiles, this is profile 2, this profile, and the study basically took analyses along this line. We don't know anything more than that. They didn't give us a lot of information as to how they took their data. However, even between the 10 years, we are seeing the same hydrogen spikes from our superficial alteration indexes and the actual hydrogen data. In the bottom profile, we're also looking at the same pattern of analyses. You can see these 3 peaks in the red data, which are mirrored in the black data. I think a lot of the, oh, I got that backwards, sorry. The red data is ours, the black data is Laren's. So once again, you can see that the data is effectively showing the same patterns. We're not looking at the same units, so you can kind of scale this how you like. We are looking at pattern recognition rather than exact numbers, and that's something to really keep in mind. We're also doing mineralogical mapping on a scale that's not been done in these areas. This little circle is about 500 meters across, and we're able to map very, very distinct mineralogical groups at the surface related to those hydrogen seeps. I'm going to show you that spectral index again. This time we have heat mapped it, and that kind of gives us a nice idea. A lot of people struggle in black and white to kind of see what we're looking at. But from this, you can kind of see that there are many, many sort of hot boundaries, I like to call them, within the fairy circles. And if we move to the next slide and put that information back, you can see the 3 peaks correlate to these kind of superficial boundaries that we're seeing on the surface. Again, here with this large peak that we see. That's very interesting, both in terms of superficial geology and mineralogy, but also in terms of what's obviously happening subsurface. Moving on to the Brazilian fairy circles, the data that was taken here was a little different. They didn't do transects, which is a little unfortunate for us, but what they did do was point measurements. I want you to look at the purple and the red circles. Those are the high values of hydrogen ppm that were taken in the field. This was taken 3 years ago. I'm not sure if that was when the data was taken, but that's when the paper was written. So we do again have a lag in time. When we apply our spectral hydrogen alteration index, we'll just call it SHA for the future, you can again see that these purple and red dots, these high hydrogen values, sit on these structural or mineralogical boundaries within the fairy circles. The other thing you can see in here is that those boundaries have become less distinct. Our theory is that these, because they are dynamic systems, they change very quickly. You see it in the vegetation. The vegetation tends to die off and then grow back after these fairy circles become extinct. If you're wondering what the blue is, that is highly vegetated areas around these fairy circles. The index that we've built takes into account vegetation suppression. So you don't need to apply an extra vegetation indices. When we then use that to mineralogically map those fairy circles, we can start to see that they are part of a much wider system. These are those 3 fairy circles in the Brazilian area. This is the area which they sit in. None of the rest of this, to our knowledge, has been explored. So this is quite an interesting system to us. We've got a huge number of fairy circles, and these look pretty active right in the north here. These are all north-south. And when we then look at the mineralogical mapping, obviously I've taken out forested areas and areas we're not interested in and layered that on top of a satellite map. But what we're interested in is these fairy circles. Again, it looks like this circle is more active, which corresponds to the Moretti data in their paper. Also, it corresponds to our spectral mapping and to the mineralogical index. So we're definitely onto something. What is really nice about the mineralogical data is that it makes sense to our story. As I said, we're pushing out a publication within the next month. If you're part of the platform, you'll hear ahead of time. I like to call it our secret sauce, so hopefully we'll be releasing that soon. And I'm going to end on the Mali Depression purely because it's one of our best examples. Mali, the data Prinzhofer, it comes from 2018. So again, we have a lag of about 5 years or more with the spectral data. However, the really key thing about this is that they had a nice transect. The annoying thing about this is that we're not quite sure how they took their transect data. So we have been very conservative in our measurements of this. And you can see our line is the red line. Prinzhofer has the yellow line. Once again, you can see these spikes at certain peaks, and you can see troughs at certain peaks. Our data lines up very well from our spectral alteration ratio as to the Prinzhofer ppm hydrogen data. So the sort of takeaway message from our spectral alteration is that we can quantifiably give you a signature of the hydrogen, not just that the fairy circles are active or extinct, but actually tell you how active they are. And I'm going to hand it back to Eiichi for the end of the presentation.
Okay, thank you, Brownie.
Welcome.
All right, so the summary. So yeah, so we looked at these 5 questions, and these are just our take. So yes, hydrogen is primary energy source. We know that, and this is a great advantage. Footprint and cost. Okay, so yeah, potentially this could be natural hydrogen's advantage, but again, it really depends on other factors, and also we don't really have a good estimate of, for example, carbon footprint, water footprint of natural hydrogen production, for its life cycle. So yeah, this is something we don't know. So that's why it's red. And the risk, yes, this is something we need to study further. There are a lot of unknowns with these risks. Where, yes, there are analogues of natural hydrogen systems already, but we do not have all the data really to understand these systems. So hopefully this information data will be published soon. Production, no, so we don't know much about it. Mali case is a only pilot project of production, and it's a small scale. We don't have any large scale production of natural hydrogen. So this is again unknown. when. So we know the components of natural hydrogen. Some of the processes we have knowledge, especially for like reservoir. We have a lot of information from hydrogen storage research, but for generation, yeah, we need more study. And how exploration we can adopt, workflows used in petroleum exploration, like exploration and also like risk management. However, the method, as we just looked at Brownie's method, we are developing methods catered for natural hydrogen exploration. So hyperspectral image analysis is one thing. Their project trying to map these subsurface source rocks using geophysics. So yeah, we are still in a learning process, and we need a better understanding of, or we need to develop mature technologies for exploration of natural hydrogen system. So the last, I have this question. You probably have already your own answers. Is natural hydrogen a game changer? I believe that natural hydrogen can be, or it has a potential to be a source of much needed low emission hydrogen. There's a potential. And even if natural hydrogen, production cannot be done at commercial, large commercial scale, Mali case showed that it can supply energy to, local communities or remote communities. So I think that is great. And also, Brownie kind of mentioned the galaxy and space. Natural hydrogen might become, energy source when we start doing space traveling. Mm-hmm. So yeah, I think there's no reason to stop, doing research on natural hydrogen. So yeah, this is the last slide I have. So if there's any question, we are happy to answer them. So.
I have a question.
Great, please go ahead.
Okay, mine's Troy Pact. Over a long career in the oil and gas business, I've probably drilled several hundred wells. If you look at hydrogen, okay, you're looking at ophiolites, you're looking at Proterozoic rocks, which means you're going to have to drill a long-reach horizontal well, and frack it, which costs a lot of money. But that is not the elephant in the room. The elephant in the room is something that nobody seems to address in these talks, and that's hydrogen embrittlement. If you look at, there's an excellent paper by Ronovich and Marchi at Sandia National Labs, and what they noticed was in pipeline steels that a pipeline steel is 30 times more likely to fracture as a function of hydrogen embrittlement, and there's a 50% chance of greater propagation of those fractures. Now, if you drill a long horizontal reach well, you've got a lot of tubulars in that well. You're probably looking at a 40-stage frac job. One break in that pipeline, and you've pretty much lost the well from the horizontal leg beyond that fracture. Then you've got the issue of transporting the hydrogen. And it turns out, quite interestingly, that it doesn't take much hydrogen in the mix to increase hydrogen embrittlement. For those who are not familiar with hydrogen embrittlement, what happens is that the H2 molecule disassociates when it comes in contact with the metal, with the steel, and it occupies the interstices within the crystalline structure of the steel. That hydrogen, and as a function of that hydrogen getting into those crystalline interstices, it embrittles the steel. Is anybody that you're aware of looking at the economics of hydrogen beyond the huge amount of money that the IRA is throwing at it, and determining whether or not, even if there is natural hydrogen, which I'm still skeptical of in commercial quantities, if it's even practical to produce it and transport it and store it, given issues with hydrogen embrittlement?
Do you want to take it? Or?
Okay, so I'll go first.
Okay.
So,
Oh, you go first. Yep.
You can go.
Okay, I'll go first. You know, we kind of have to leave a lot of this science to the people after us. We're tackling such a huge problem in terms of the characterization of natural hydrogen itself that we are not set up to look at the economics. Having said that, I believe there's going to be a push in the government to then look at that. We've seen the early stages of government funding for hydrogen and critical minerals, and the next, logical state would be to then look at the economics of it. I'd be interested to see whether the Gardner Policy Institute here at the University of Utah is looking at it. I may reach out to them and see. In terms of storage, we do have things like the ACES Delta plant, which is down in southern Utah or central eastern Utah, western Utah. And they're looking at hydrogen electrolysis, whether that can be used to sort of inform us more on how to transport hydrogen. I'm not sure. There are a lot of problems with hydrogen. I mean, it is a itty bitty tiny thing that we have a problem capturing because it moves through everything. You've seen on the hyperspectral imaging, a lot of these fairy circles have salt coming out of them. And that's not by chance, right? Salt is a really good cap seal for hydrogen. And so maybe we look to the natural environment to try and work out how to transport this in our world on the surface. So I'm going to hand over to Eiichi for his thoughts.
So with regard to project or group working on economics, I believe that there's a group working on the economics of hydrogen at the University of Houston. I think they had a large kind of a symposium this year in April, so you can find their probably presentations there. And also ARPA-E.
Wait a minute. Who's the? Go back if you would, please. What's the group that's working on economics?
University of Houston. If you search for a hydrogen symposium, University of Houston, you can find their symposium and group people working on economics there. And ARPA-E also, along with the 16 project on stimulation of natural hydrogen production, they also awarded a grant to one of the national laboratory here to look at life cycle of natural hydrogen production. And I think the economic analysis is part of that project. So you can also look up that.
Okay.
Project. Yeah. And also the transportation, I think it really depends on the scale of production project. It can be used locally, and then you don't need to really transport hydrogen. And also
transport's a huge issue because many of the areas where you're looking for natural hydrogen, if they do exist, are quite remote. And so you're talking about a large miles and miles of pipeline, all of which would have to be organic, sleeved either with plastics or some sort of organic coating.
Yes.
And those don't exist right now. No tubulars for drilling and production that are coated exist. So there's some huge issues.
Yes, I totally agree.
Yeah.
And but these ongoing exploration and drilling for natural hydrogen would I believe that facilitates the development of new technologies. So I want to stay optimistic, and I trust that our engineers can come up with new inventions.
Yeah. We're geologists. I like to think that we find the rocks and then we pass the information on to the engineers who are far better at what they do than we do, in terms of transport and things. And hopefully we can do our job and find the hydrogen very well, and then they can do their jobs and transport it really well. So I think staying optimistic is very useful with this, just because it is such a new technologies, new frontier of research. If there's not sort of the positivity behind it, I'm not sure it will continue to get traction, which would be sad because it's very interesting.
Okay.
Bryony and H, we also have another question in the chat. Are you able to see that, or would you like me to read it off to you?
Is it, can you please clarify at what depth was natural hydrogen encountered in the Scott and D2 exploratory wells in Kansas? And then a sub-question, in what concentrations was it commercially quantifiable?
So the hydrogen, so yeah, I'll be quick. So you can see that the gas 1 and 2, these are, yeah, so these are the points where where they encounter natural hydrogen. And concentration was it commercial quantity. Okay, so again, it really depends on how deep your well is, and also associated gas. If you have helium, large quantity of helium, then I think hydrogen becomes more like a sub-product, and then the concentration, it really depends on many factors. So I cannot know. So this is again something that we need to analyze.
Unfortunately, a lot of the papers that are coming out on hydrogen have not been clear about their methods. A lot of people are obviously trying to keep their IP to themselves to be able to continue their research. What we're hoping to do is put everything we have out to our sponsored companies and obviously in publications. So I think that's key with this work that we're doing. We really are looking for collaborative partners who think they're up to this. So if, reach out to us if you do have ideas, or if you have ways that you think this project would be a good way to go.
Okay, well, thank you, H and Bryony. If there aren't any more questions, as you can see on the slide here, we have another webinar coming up on November 7th with Dr. Milandev. He is professor of chemical engineering and EGI director here at the U. I put his registration link in the chat box here. Again, thank you for joining us today. This will be available to watch later. We will get it up on our YouTube channel.
Jennifer, before you sign off, I do have a question. I think Sudeep also has a question, if you don't mind.
Oh, yes. Perfect. Yeah. Well, status.
Okay, then I'll
go ahead.
I'll go ahead and ask my question. So it's been an insightful presentation indeed. My name is Joseph Lai Tetelai. I'm with the Ghana National Petroleum Corporation, where I am a lead geologist. Recently, we've been looking at one of our onshore basins. Is called the Voltairean Basin. It's approximately 104,000 square kilometers. It covers about 40% of the landmass of Ghana. And we are doing some initial exploration for oil and gas, but we are also looking at trying to see if we can get some hydrogen occurrence within that particular basin. So this is very insightful and has been very helpful. I have some few questions. If I heard Eiichi right, he said that in the Malian field, the pressure has not decreased. If I heard him right, I would just want to find out why, because I expect that once they are using it to power their homes, the pressures will be decreasing. So is there anything that is sustaining the subsurface pressure? And then I want to ask Bjorn.
Oh yeah, go ahead.
Okay, I want to ask all my questions so that you can answer. Then Bjorn, you talked about Sentinel-2. I know Aster is free. The images from Aster is free. I just want to also find out whether the images from Sentinel-2 is free and is something that can be easily accessed by anyone who is interested. You also talked about the depressions or the fairy circles. Are these always associated with hydrogen gas? I mean, is it something that is symbolic of identifying hydrogen gas? Is it something that anytime you see that, then it means that there's a potential of having hydrogen gas within that area? And my last question was, I wrote here, are you able to distinguish between active and non-active ferrocycle? I think that you have answered that one, so that is fine. So these are my questions, please. Thank you.
Okay, so let's start with the pressure. We're not entirely sure. It could be that it's just a very large system and we haven't seen a pressure drop because we really just haven't tapped the system enough to impact it. I think that's probably the most viable answer we have at present. It also could be relative to recharge of the system. These systems are incredibly dynamic. And so, as you asked about active and extinct, we're pretty certain that we know which are active and which are extinct, and they obviously have these dynamic changes over decades, which is wild in geology. So hopefully that answers a little bit of that. Your next question about Sentinel-2. Sentinel-2 data is completely free. I would advise you to look up the Copernicus browser, which is related to the European Space Agency. Sentinel-2 is a European Space Agency satellite. There are also other Sentinel satellites, but I personally find Sentinel-2 to be the most useful with mineralogical or hydrogen exploration. You can also look up any of the other satellites. ASTA-2 is free, but when you're looking at ASTA data, don't forget that it's an old satellite that essentially became defunct in about 2008 when it lost the ability to take shortwave infrared information. So Sentinel-2 is an excellent satellite. You can also use Landsat, but Landsat has fairly large gaps in its bands. The best one, as I said, is Avaris. That's 224 hyperspectral bands, so it covers a very wide range. Try using Sentinel-2. You are more than welcome to reach out to Eiichi or myself. We are happy to provide more information about how to access things like that. We are a university, and so we look to help people just as much as we look for research funding. Your last question was about whether we can quantifiably look at extinct or viable circles. We've gone one step further. We can actually tell you areas of the ferrocircle that are likely to be producing hydrogen and in what quantities. And that's having compared in publications and publication data to our spectral indices that we've developed. Your other question about whether all these little circles are hydrogen, no, absolutely not. You get a lot of circular depressions all over the world for many, many different reasons. For example, in England, you can get these circles caused by fungus. They're often mistaken for crop circles, in fact. So it's just because you have a depression does not mean there's hydrogen or helium. So I hope that answered all your questions. Please reach out to us if you have any further ones.
All right. I'm happy with your answers. Thank you so much.
Great.
Thank you everyone again for joining us today. Again, I put the questions can be sent to contact egi@egi.utah.edu. I also put Briany's and H's emails in the chat for you to send any questions to them directly. Okay, well, thank you everyone again for joining us today. Anything else from our speakers?
Just as you said, please reach out if you have any questions or comments or you have ideas. This is really the forefront of science right now, and that's incredibly exciting. But that also means that there's a lot of wiggle room for different aspects of science and different ideas around this. So thank you everybody for tuning in.
Okay, thank you everyone.
Thank you. Bye.
Thank you. Bye-bye.